So let's start the session then. Um, Hello everyone, I'm Sai Venkatakrishnan, a PhD scholar in the Department of Computer Science and Engineering at IIT Madras. So this is week 4 live session for the course Blockchain Fundamentals. The agenda would be we'll be discussing any queries you have pertaining to any of the week lectures, and we'll be answering, we'll be discussing those queries. So you can either unmute yourself and post your queries, or you can post it in the chat window. Okay. So first, any queries you have? Any queries in Bitcoin or the Ethereum blockchain platform? Hello?
Yeah, yeah, we can hear you. I don't know if you can just revise one more thing regarding, say there are like, suppose we make a payment, right? Uh, we make the payment using the hash of the public key of the recipient,
Right.
right? And then there is a SIG, some SIG function that is also there to validate when you want to redeem actually.
SIG fund.
Uh,
Okay.
yes, yes. So if we can just explain again that part using, there are some stack was there, different operation was there, how that's
Okay.
whenever
Okay.
you find time. Yeah.
Yeah. No, so actually, this session I have materials to discuss, but I wanted it to be, instead of like a one-way thing, I wanted it to be interactive. So like I wanted to first um, um, z- zero in on the doubts that you want to have and explain those first, and get the base ready before I explain the other content. So I have some contents as in like how folks work in Bitcoin and like how Ethereum is different from Bitcoin, but which are not discussed in the video lectures. But as far as this course is concerned, we need not go into too depth with respect to Bitcoin and Ethereum. But if we find time, we'll go into that. But first, I wanted to know whether we have queries and answer those queries first. So anyone, like however named the query is, like just feel free to shoot up the questions, because this whole Bitcoin thing is sort of like this blockchain thing is like slightly confusing, as in like the solution is not direct, and they have used multitude of technical concepts to arrive at these solutions. Okay, so it's um, it's fair enough that you will have so many doubts, and I expect those doubts actually. Okay.
Hello, sir.
Yeah.
Good evening, Sai, sir.
Yeah.
Yeah, Sham, yes, sir. Actually, one doubt I have
Yeah.
regarding Bitcoin mining. Sir, in that lecture, professor told that liveness has been given priority over safety.
Okay.
So, in that, they told in Bitcoin, in every 10 minutes around, one block is created.
Yeah.
So, I have one doubt that suppose one miner is there, he's mining that block, and suppose if he's not able to mine that block in 10 minutes.
Okay.
So in that case, how it will be, or other way, like suppose that block is mined less than 10 minutes. Suppose if it is mined in 3 minutes or 4 minutes. So how this lineless property is ensured here in that case?
Mm, okay. Okay. So I guess your question is, how do they ensure it comes every 10 minutes, right?
Yeah, every 10 minutes, correct.
Ah.
So that in lecture, professor told us that every 10 minutes means liveness means in fixed duration block is created.
Yeah. Yeah.
So how it is ensured? Suppose one miner is there and they are creating block. Suppose some miners they created block faster than
Hmm.
within 10 minutes they created the block. Then how it is ensured that after 10 minutes only it will be created? And suppose some miner is not able to create that block in 10 minutes,
Okay.
eh, that person is taking more than 10 minutes. Then how would this property is ensured?
Yeah, okay, good question. I'll answer that. Okay. Any other questions like you have? I'll answer it in this order. Anyone else? Did everyone understand how the UTXO model and those things? Okay. So in that case, I'll start answering um, the first question. Okay. So the question was to re-explain or revise the concept of how a transaction works and what is being signed and all those things. Okay. So let me use my previous slide. So when I tell, say like, uh, so I guess I assume everyone understood how the Bitcoin address of a user is generated in this Bitcoin network. Everyone understood that, right? If you had attended my previous live session, I would have explained it. So is there any doubt in that section?
I missed that actually, but I understand
Okay,
there will be several public and private keys, not just one.
right.
Uh, yeah.
Right. So just a quick review, right? You won't have the notion of a username, as in like if you go into a bank, how will the bank identify you? You will have a account holder ID, you will have a username, all those things, right? But in Bitcoin, it's not like that. Instead, everything in any blockchain, this cryptocurrency network, um, anonymity was the key thing, at least pseudonymity was the key thing to achieve for with respect to privacy, since everything is decentralized, right? So they don't use user names, all those things. Instead, the key thing that is being used to identify you is your public key. So for every user can have multiple public plus private key pairs. Okay, and the private key is the one which tells you're the owner, which asserts you. Okay, and this public key is the identity which you reveal to the network. So these are the public identities, and this public key is the owner of this private key. Okay, so this is how in Bitcoin it works, and the Bitcoin address is nothing but you apply hash to this public key and you get a 160 bit address, which will be your public key hash, PKH. So and this will be your public key hash address, and say if two persons, Akshay wants to send 10 bitcoins to Ganesh, then he would be using the address to which he would be sending it. So similar to a bank, he will be sending it from address. So the two address actually. So the two address would be this public key hash of Ganesh. So Ganesh might have like multiple public key and private key pairs. Out of that, he will tell Akshay to send it to one specific address. So as in Ganesh should be having multiple accounts. Okay, so when I tell accounts, don't treat it as an actual account, but it's just like treat it as like in your wallet. If you take your purse, right, you will have those multiple pockets within your purse, right? Like you will be placing in one thing like 100 rupee notes and the other 10 rupee notes and all those things. So in the same way, assume that Ganesh is having a software like a wallet, and this wallet will be maintaining a set of public and private key pairs. Okay, and Akshay can send this 10 bitcoins to any of one of these public key addresses which Ganesh owns using his private key. Okay, and the wallet would be this wallet software is something which Ganesh should be using, so that has access to the, which maintains these private keys and all those things. Okay, so when we tell Akshay wants to send 10 bitcoins, he has to generate a transaction where there will be two parts. One is the input part, the other is the output. And in the input part, he should specify to which coins he is using previously. So in the input part, he should specify two things. One is the previous transaction ID and the previous out index, and the other thing is script sig. So what this input actually means is, in a Bitcoin there is something called as it follows the UTXO model. So the Bitcoin is, if you look at Bitcoin, it's just nothing but a series of transactions. Say Akshay is a miner. Um, he has previously some 25 bitcoins in his account. Okay, so this should be uh, a part of a transaction, and here in the previous transaction output, it should have Akshay's public key address. Okay, and the index of the output is 0. Okay, so now out of these 25 bitcoins, Akshay wants to send 10 bitcoins to Ganesh. Means he will be using this previous transaction ID to refer to this previous transaction. Okay, and the out index is 0, so he's referring to this output he had received, and this will be your input, and the output is nothing but the two address to whom he should send, which is he should specify the 160 bit address of Ganesh's public key hash, and he should specify the conditions, which is the script output. And these conditions should be specified in such a way that it's a series of instructions which enforces the rule that only Ganesh can use these 10 bitcoins and no one else can. So that's what the script output will be having. So it's just a series of instructions, and the script sig is something which Akshay should uh, populate, and the script sig is nothing but he takes this whole transaction, okay, this whole message, and he signs it using this private key. Okay, and so when he signs this using his private key, that will be the script sig. And this private key, whatever he signs it, right, the corresponding public key should have been used in the previous transaction that Akshay is referring to over here. So in this, the output, right, Akshay's public key hash, the corresponding private key only should be used to sign this transaction. So when a node receives this transaction over here, transaction 1, okay, it will check whether Akshay is the owner of this 25 bitcoins specified in this previous transaction 0. Okay, and so this transaction over here will also have a script output. Okay, so the script output would be given this script signature as input, and if this condition works right, then this transaction 1 is valid, and there will be a new set of outputs created in your UTXO set. And this new set of this UTXO set is nothing but the unspent transaction output. So every transaction will have an input and an output. The input specifies the previous output it will be consuming, and the output specifies the new outputs that are created. And the UTXO set is nothing but whatever transaction output is still unspent, or it's still not part used as an input in a new transaction, those all will be stored in this database, in this UTXO set. So before transaction 1 was given to a node, right, this transaction zero's first output, which is at index 0, that would be present in the UTXO set. So it would be like transaction 0, 0 output is in the UTXO set. And when the node sees this transaction 1, it will confirm that this transaction 0's 0 output is can be used by Akshay using the script output. It runs the instructions, and once it identifies that, right, once it satisfies, it will remove this output from the UTXO set and tell this transaction 1 was a success. Okay, this is a success, it will tell, and it will add the new output, which is transaction 1 0, and this transaction 1 0 will have a new so it will have a different script output such that only Ganesh can use it. So like that, when Ganesh later creates a new transaction and uses this 10 bitcoins, whatever he got from Akshay, to send 5 bitcoins to uh, Bob or someone, right? So then this transaction 1 0 would be deleted, and in its place, what will come is the transaction two's output, and this transaction 2 output would be can only be used by Bob. Okay, so this is the high level overview of the
Uh,
UTXO set. Yeah.
yeah. One thing I didn't get is script sake. I think you are talking about transaction one, which Akshay received.
Yeah.
Uh, uh, okay, I think let's say that we'll not talk about. My only intention is that say even output also script sig will be included. When Akshay sends 10 bitcoins uh, to I don't know whom you said. Okay, say Ganesh.
Yeah.
Yeah. So then Akshay also has to include script. That's what I remember. Script sig in the output, so that Ganesh, when he receives this 10 Bitcoin, he can only decode his script sig. He can decode using his private key and he can validate. He can claim that okay, this is only Ganesh can do. My only doubt was that how Akshay will be able to generate script sig for Ganesh. I think in output even
Okay.
script sig
Okay.
will come.
Oh, okay. Okay. So see, I'll just erase these. Okay.
Output script sig will also appear right in the output column.
So in a UTXO set, right, it stores the transaction outputs. Okay, and a transaction might have multiple outputs. So here the first output, this is at index 0, and this tells the 160-bit address of Ganesh to whom Akshay is sending, and it will have the amount, which is 10 bitcoins he is sending to Ganesh, and he will have the script output. So all these things, the amount, the true address, and the script output, these things together form your transaction output, which will be stored in your UTXO transaction 1 0 index will point to this. Okay, so this entry would be stored in your UTXO. The script sig, okay, the script sig is not with respect to this script output. You should understand that this script signature is with respect to the previous transaction output, which Akshay has control of. We assume that Akshay was a miner and he had some 25 bitcoins, right? Say this is transaction 0. Okay, so there will be another entry previously, which is like transaction 0 0, and the amount would be like 25 bitcoins.
Who generates that
Yeah,
script sig
which
transaction?
this one.
I got it. Previous transaction. Who generates it? Let's say, okay, we'll go back talk about the previous. Let's say Bob has sent 10 bitcoins to Akshay,
Okay.
right?
Okay.
So now in this process, see, right now, I think you are saying that, okay, previous transaction for Akshay is the history
Mine.
of who transferred 10 bitcoins and script sig is there, right?
Yeah.
But question is who generated this script sig?
Okay. See, the when you the script sig. Okay, first understand what the script sig is used for. The script sig is generated using your private key. Okay, and this private key you will use it to unlock an output that you own. Okay, get that point? The script sig would be used by Akshay to unlock a previous output. So the script sig in transaction 1 is generated by Akshay to unlock his previous output that he owned, which Bob sent it to Akshay. Now Bob, in his script sig, in order to send 10 bitcoins to Akshay, you would have used a script sig over here, this input. Okay, this input would be unlocking the Bob's output. Say Bob received from someone else 25 bitcoins. That output Bob would be unlocking using this script sig.
Okay.
So the key thing to note is your script output, which is with respect to the current transactions output. The script sig is used to prove that only you are the owner of a previous transactions output that you want to use now. It has nothing to do with Ganesh. It just asserts the condition that I am the real owner of the 10 bitcoins that Bob sent me. So just assume like this cryptsig is a password, right? You want to
Okay.
transfer 10 bitcoins to Ganesh, means Akshay wants to transfer. He has to first log in into his bank account and then do a transfer. So in the
Okay.
same way, this cryptsig is the password for login. And that password, how they have done is every transaction output will have a script output. And when I apply the script sig to the script output as input, right? It will evaluate to true, and when it evaluates to true, it tells that okay, whoever is using this referring to this transaction, previous transaction, he is indeed the owner of that transaction output, and he can so the transaction 1 is valid and he can send this much amount of bitcoins to Ganesh. That's what this scripting is used for.
Okay. And one more in these conversations, the key size you said that hash is 160 bit.
Yeah.
Uh, are you using RSA or uh, what kind of pair, public and private key pair you're using?
Sorry, I didn't get it.
The you say the hash of the public key is 160 bit,
Yeah.
right? Uh, so uh, I'm lost there actually. Hash you are taking 256 hash, right? Or
Okay.
why
So
160 bit? Public key and RSA public key size is
yeah.
around 2048, right?
So that
That's the
public key 2048 bits. What how it is generated is we first apply SHA-256. Okay. And to this output we apply something another hash called the RIPE MD160. Okay. So the final output is this is 160 bits, and this
okay.
is your hash. So actually this is your address, uh, the public key hash. The reason why public key hash is being used is one, you don't want to directly reveal your public key, like there might be attempts to find your private key or something like that. And the other important thing is your instead of storing 2048 bits in this output, right?
Yeah, I understood.
Storing 160 bits hash is efficient. The reason being, this output, every transaction's output would be part of your UTXO set. And this UTXO set should be maintained by all your minor nodes and full nodes in the Bitcoin network. And instead of 160 bit, if I'm storing 2048 bits, right, it's like what 2x increase of memory storage. So that's a clear like efficient approach where they store this 160 bits hash instead of the direct public key. And
Okay.
yeah,
Yeah. Okay.
and the sample output script evaluation. One second, I had it over here. So this will be your script output. This will be the instructions. Okay, and this will be your input. Okay, so the script output would be the conditions for say Akshay wants to spend 10 bitcoins. Okay, so this will be the conditions to certify that Akshay is the owner, that and only Akshay can uh, have control of this output. Okay, and this input would be such that only Akshay can generate, and for this they make use of public and private key. And how they make use of it is, the script sig is the what they do is, Akshay, when generating a new transaction to consume the previous outputs, right, he will sign this transaction and generate this script sig, this signature. And signing the transaction means he will be signing it, you'll be using the encrypt function, using the private key and the transaction message, and that will give a message say yes. Okay, and what the condition would be is, the condition would be when I decrypt this signature yes, using the public key whatever is mentioned over in this condition over here. Okay, so this public key, if I decrypt it, it should give me the same transaction which I had used over here. So this both should be equal. So in that case, I am asserted the condition that the output has to be paid to this public key, and since Akshay is having the since that person is having the private key, he is the rightful owner of the transaction output having an amount of 10 bitcoins. So this operation is only specified in this script key output, this instruction set. So this so they are using a stack model of execution. Okay, I guess professor would have explained it in a visual way how these things get pushed into and popped out. And this op underscore things are there, right? Op underscore loop and op, so these are nothing but operations which are allowed within this script output or script public key. And two inputs would be provided as part of a script sig which Akshay would be generating to use his outputs. One would be the signature of this transaction, which is this one, encrypted with your private key. And the second thing is the actual public key, which is like 2048 bits. And why Akshay is specifying his public key is also because if you remember, only the 160-bit hash of the public key would be stored in the output. So step one for the script output is to certify that the hash, when I apply hash to this public key, the double hash, that is equivalent to the hash of public key which is being stored in the uh, transaction output. So this is what this step over here, this operation over here denotes. Okay, so first what they do is they apply the hash operation on this public key, and they verify whether this hash is equal to the one which is stored in the output, transaction output. That's the first condition. And the second condition is, once they verify it's equal, right, using this public key over here, they will decrypt the signature. They will decrypt the signature and check whether it's the same transaction contents which is being forwarded to each node. And if that's the case, then they uh, ensure that the private key is the owner of that public key, and they validate the transaction and it evaluates the truth. So this is how script public key and script sig works. And you can argue like, why not a simpler so why are they storing all these things as part of the transaction output, these instructions? All is by every transaction output is specifies the amount, the bitcoins it represents, and also the conditions to unlock that output. Only Akshay can use or only Ganesh can use using his private key. So these two things together only will ensure that only a person or like a set of individuals can use that specific transaction output. And Bitcoin as such is everything is just nothing but a set of outputs only, nothing more. And the cool thing with script pub key is instead of having a single signature, you can have a condition say like only if Akshay and two others out of five people come together and they should sign a transaction, and they three together only can unlock this specific transaction output. So those are called as like multi-sig. Say like you have a company and it has like some funds, you don't want to give the chairman the single like the private key. Instead you can you can create a transaction output such that not only the chairman but like all the board of directors, at least a majority of them should sign a transaction, then only the funds would be unlocked and can be transferred to someone else. So like that all those types of transactions are also allowed. It is called like multi-signature. And so in that case the script public key would be different, these instructions would be different, because instead of checking one signature they will be checking multiple signatures and verifying whether the transaction is valid or not. Okay, so any doubts in this transactions signing?
No, it's okay.
Okay, so in that case the first question is answered. uh, let's go move to the second question, which is mining duration. So the if you Google about Bitcoin mining duration or like how the blocks are being added, it is the usual thing is they will mention it is like 10 minutes every one block every 10 minutes. Okay, but the actual and you but the actual algorithm, right? How it works is let me reuse my slides. Yes. Okay. So the actual rule in Bitcoin is as follows, which is the rule in Bitcoin is right. It don't be directly ensuring one. It won't be ensuring one block every 10 minutes. This is something which is easy to understand, but this is not the correct way where how Bitcoin works. Okay, the way how Bitcoins work is everyone knows how this proof of work concept, right? In Bitcoin, you would have studied by now, right?
Yeah, yes,
Yeah.
yeah.
So in the Bitcoin thing, there is a target value where a set of zeros, some say n zeros are there, and whatever hash the miner generates the hash. Okay, you should find a nonce and the hash of all the transactions, which is the Merkle root. Okay, so the Merkle root of all the transactions, you should find a specific nonce and the hash, previous block hash. Okay, so all these things together should be less than the target, and this is your proof of work. Okay, and so this target, setting this target or changing the difficulty of this target, if I decrease the target, right, then it will have a more number of zeros and it will be more difficult to find the corresponding hash. And if I increase the target number, the target is nothing but a number. If I increase the target, right, the difficulty will actually decrease if I increase the target, and if I decrease the target, the difficulty increases. So by difficulty, what I mean is the time taken for a minor node to find a nonce value such that this condition is satisfied. the proof of work condition, right? So increasing or decreasing the target changes the difficulty, which in turn will affect uh, the duration between every block which is being added to your blockchain. And the code in your Bitcoin client. Okay, so the question you should be asking is, this target is a number. Who is setting this target in the first place? Is it like some central server is there, which just tells like, okay, the target is fixed to some value, or how is it being set? Is every Bitcoin, every node in your Bitcoin network, okay, so every node in your Bitcoin network would be running the Bitcoin client software, and that software will have a rule. And what the rule would be is uh, this difficulty rule, they mention it. Okay, so they look at the last 2016 blocks. Okay, so whenever a miner has to mine a node, right, or say a miner the blocks are being mined, and the last 2016 blocks are there. Okay, and this is the head of the blockchain. Okay, so they will look at the last 2016 blocks, and they will see the duration during which these 2016 blocks were mined. So say this was mined on a Thursday someday, and the zeroth block of the 2016 range blocks, and that was mined say like 3 weeks back. Okay, the rule is that if the last 2016 block were mined in a duration more than 2 weeks, then it was the case that my difficulty was too high, and the miners were feeling difficult to uh, successfully find a nonce to satisfy the proof of work condition. And in that case, what they will do is they will decrease the difficulty and increase the target number. They will increase it. Okay, uh, and if the last 2016 block were mined in less than 2 weeks, right, then your difficulty will increase and make it tougher for the miners to find the nonce and mine new blocks. And so this is the actual condition which every node follows. They will look at the last 2016 blocks, and they will see whether it is mined within 2 weeks or not. And if you look at divide the block count with the seconds count, right? So 2 weeks means like 2 into some 60, what, 2 into like so many days, and convert this 2 weeks into number of minutes, right? If you divide that count, it approximates to one block per 10 minutes. So this is what everyone would be telling, like one block 10 minutes is the block, every block would be added. And the real rule which is being followed is that the last 2016 blocks should be mined in 2 weeks. So that is the actual rule, and based on that only we arrived at this output, which is one block every 10 minutes. Okay, so this is the actual rule which is implemented in the Bitcoin software. And say 2016 blocks are present, and what every miner will do is before mining a new block, right? Say a miner gets some 1,000 transactions. Okay, so if a miner gets some 1,000 transactions, what a miner will do is he will find a nonce such that it will be less than some target value. And what the target value should be is how the miner will get to know is he should determine it uh, themselves. They should determine it based on seeing the last 2016 blocks. So if they see that the last 2016 blocks was in a less time period or more time period, right, they should set the target accordingly. Okay, they should set the uh, uh, they will see whether the target was decreased previously or not, and they should follow the follow a target value such that the previous block was also accepted with that same target value, and try to achieve that uh, condition in the proof of work. And so it's up to the miner to follow these three rules to set the target value and find a nonce such that it's satisfied at less than target value condition. And when it propagate this block to all the other nodes will see whether this target value is in sync with the previous block's target value, or whether the miner has reduced the difficulty and increased the increase the target value and made it easy for them to mine a new block. So all these things are part of the block validation rules. So this target thing right over here is Merkle root, difficulty, and target. So these things they specify in the block header, and every node should every mining node or every full node, while they validate the block, they will see to that the target value which the miner satisfies is in sync with the previous block's target value, and they don't erroneously like increase it simply. So do you get the idea? Hello?
Yeah, understood. I don't know the person who asked.
Sorry.
I understood, yeah, but I don't know who had asked that questions. Yeah, I understood.
Okay, I guess
Uh,
Shyam or someone
Yeah,
asked.
yeah, I asked. Thank you, sir. I got it.
Yeah, okay.
I have some follow-up question on the similar topic. Can I ask, or
Yeah,
I'll
yeah,
ask
sure.
at them?
Yeah, you can ask now.
Okay. See, so you understand that it is possible that two miners can generate a block simultaneously.
Yeah,
It can happen, uh, and because of that, the fork branch gets created, right?
right,
The Bitcoin, the fork branch gets created, and I also understand that. So the two branch may continue up to certain period
right,
till one branch becomes more long than the other,
right.
and then the other one is discarded. Uh, right. I think there are some rule is that some six up to six blocks we should create before the transaction is considered as confirmed or
Yeah,
something.
yeah.
If I remember. Okay, my question was suppose whichever branch is discarded. So
Okay.
there are some blocks or some transactions are added.
Yeah, yeah.
Now, when they are discarded, so are there any tally
They are
to
called as
check,
orphan blocks or orphaned transactions. And
yeah, whether they will be added back to some other
yeah,
block?
yeah. So what
How do
every
you ensure that?
yeah.
Yeah,
No, so every how they will ensure that is every block would be every node would be maintaining something called as the mempool. And when you tell um, see when say if a fork had occurred over like this, and okay, so according to you this block would be discarded because this is the longest chain. Okay, so when I tell discarded means the set of nodes which are assuming this block to be here as the longest chain, right, as the head of the chain, they would have seen this new chain over here, and they would have see like, okay, the height is 4, whereas in this the height is 6, the chain height. So this is the longest chain height, and they will switch to this block, but they won't directly discard this block, as in they will get all these transactions over here, and they will try to mine a new block and add it at the end. So it won't be lost, those
Oh,
transactions. So they will add it to the list of unconfirmed transactions every node, and the miners will be so the miners, right? When you tell like this block would be deleted, it won't be deleted. It won't be considered as part of the longest chain, but there will be nodes which will be maintaining these branches all. Okay, and those nodes would be like say full nodes or mining nodes, especially these minor nodes. And what these minor nodes can do is all these transactions which are unconfirmed, right, which were deleted, they will try to again use these transactions and mine a new block at the start, and later they will delete these parts. So every node, the proof of work, the main thing which is considered is the longest chain. But when you tell it's deleted, right, it won't be actually deleted all these forked branches. Instead, it will be present as part of your storage or something. It's only that you will be just looking at the longest chain for any valid transaction set. This the other blocks, they will get the transactions out of it and delete it. So a block is nothing but list of transactions only, right? So they will be storing those unconfirmed transactions and reusing it until it gets
oh,
confirmed. And why I tell reusing a block, reusing those unconfirmed transactions, right? If you see over here, the nonce in the block header specifies your that the nonce that the miner should find such that the proof of work less than target is satisfied. Okay, and this nonce, if you see, it is just 4 bytes, which is 32 bits. But if you notice the target value, right, it will be like around 100 zeros should be there, which means 100 bits, 2 per 100 minimum iterations you should be going on average in order to find a nonce such that it is less than the target value. Okay, and but here you just have the nonce as 32 bits, which means only 2 per 32 iterations you will be going within this nonce space. And the ASIC things, right, those specific mining chips, they have become so powerful that these 2 per 32 iterations, they go within 1 second. And now what happens is within 1 second they would have exhausted, they would have gone through all the values of the nonce, they would have hashed every possible 32-bit value of this nonce along with the Merkle tree root and the previous block hash, and they would have come at a conclusion that this condition less than the target value is not satisfied. So now what should they do? They have iterated through all the possible nonce values, but what can they do more in order to satisfy this target value? So what they will do is these, say there are some 2000 unconfirmed transactions, right? They will swap some transactions out and bring in some new transactions, recalculate the Merkle tree, and again go through all the 32-bit nonce values. So to find, to prove that, to achieve this proof of work condition less than the target, not only the nonce field is being used, but also the transactions would be changed randomly to arrive at to satisfy this condition by the miner. So for those purposes, all these unconfirmed transactions that they have, right, as in those branches, the miners would be having all those things in a database called mempool, which is memory pool. And in those things there will be the unconfirmed transactions which they will be trying to use and trying to satisfy this less than target condition. Okay.
yeah.
Hello.
Yeah,
Can you please elaborate the function from a problem of double spending? How we can eliminate the problem of double spending?
right. So in double spending, how it is eliminated? Okay, so even in the forums, one student had asked, cryptographically only double spending is eliminated, all those things. The key thing is double spending is eliminated using the consensus rule and not via your cryptography or cryptographic keys. What I mean by this is when you generate a new transaction, though the transaction output should be populated in your UTXO set. Okay, so it will be having the all the transaction outputs. Okay, and whenever you want to spend a Bitcoin or something, which is nothing but you refer to a particular transaction output index and provide your private key signed the transaction as input, and it will validate the transaction. So this is how the usual spending works. Now double spending, what is the meaning of double spending is, say you have in one transaction, one is there, and say transaction 2 is referring to this transaction 1's output. So transaction 2 is spending transaction 1's output, means I should not use another transaction 3 which spends the same transaction 1's output which is being spent by transaction 2. So this is what double spending. Sorry, hello. Did anyone have any question in between?
No, I think you can go ahead. I think somebody by mistake just unmute her.
Okay, good. So this is what double spending is. And in a physical world, this double spending is automatically prevented because you will have a physical currency note, and once you so here actually the culprit is the one who is owning these transaction output. Say Akshay is the owner of transaction one's output, right? Akshay, he would be the culprit because he's trying to use that output in two transactions. So he has 10 rupees, means he's trying to spend those 10 rupees to two people at the same time or in different times. He's referring to that same 10 rupees. In a physical world, that won't be possible because when Akshay can give that physical note either to Ganesh or Mahesh only, because once he has given, he loses ownership of that 10 rupee physical note. He doesn't have it anymore. So that is automatically solved in the physical world. But in the digital world, uh, you using this private and public key, what you assert is Akshay is the owner of this transaction output. I am asserting that condition using the private key and public key. But to prevent Akshay from reusing this transaction output and ensuring that he spends it only once, that will be ensured by all the nodes in the network um, maintaining this UTXO set. How they will ensure is, uh, say some nodes, say like Akshay sends 10 bitcoins in transaction 2 to Ganesh using this transaction 1 the output, and the same transaction 1 output is sending it to Mahesh. Okay, and this one to Ganesh. Okay, what will happen is, say this if what will happen is, two things might happen. These two transactions might be part of one block, the same block, or it might be part of different blocks. Okay, these two conditions might happen. If both are part of the same block, it don't happen because the transaction validation, say 1000 transactions are there, means in each block, every node when it receives a block or when it receives a block, right, it will um, it will see to that when it say there was this transaction one in the UTXO set is still unspent at the beginning, and within the same block, say at some point at say 501 transaction was this transaction 2 is there, and after some points transaction 3 was there. Okay, and what happens is every node will go through the will execute each transaction sequentially from the starting, and what it will do is it will update this UTXO set. Okay, and when it reaches transaction 2, what it will do is it will see, okay, transaction 2 is using up this transaction 1's output, and it will remove this transaction 1 output from the UTXO set, and it will tell that this transaction 2 is valid, and it will go. And when it reaches transaction 3, what happens is it will see that transaction 3 is referring to some output called transaction 1, which is not present in the UTXO set, which was removed previously by transaction 2, and it will see that this transaction 3 is invalid. And if this
Yeah, but it
transaction, sorry,
yeah, but it may happen that Akshay got 15 BTC. He gave 10 to Ganesh and 5 to Mahesh.
uh,
That is not.
he gave 5 to
Akshay got
ah,
Akshay got 15 BTC in transaction 1. He gave 10 to Ganesh, 10
okay.
BTC to Ganesh, and 5 to Mahesh. That's a valid transaction. It's not double spending. But
He
as
has
per
15.
this theory, as per this,
Ah,
then the Mahesh transaction will it fail?
no, that won't fail. See, one thing to note is whether he's um, reusing the same output in two transactions. Okay, so when you tell that Ganesh is sending, sorry, Akshay is sending 10 to Ganesh and 5 to Magesh, in two ways he can send it. Okay, one as part of the same transaction itself. How means this transaction 1 is referring to, which is having 15 bitcoins as input, and in this output 0 and output 1. This output 0 is for the Ganesh, which is 10 bitcoins, and the output 1 is for the Mahesh, which is 5 bitcoins. This is valid because here is referring to only one transaction, previous transaction output, which is transaction 1's output. Okay, this is one way of splitting it, that 15 bitcoins. The other way is Ganesh can have uh, two transactions such that the first one is sending it to sorry, Akshay can have two transactions. The first one is sending Ganesh 10 bitcoins, that is output 1, and the remaining 5 bitcoins is sending it to himself to some other public address, which is owned by Akshay itself again. Okay, so this will be the previous thing. And the second transaction, what Akshay can do is these 5 bitcoins, he can refer to it in the previous transaction output and send the 5 bitcoins to Mahesh. So this is a set of two transactions, and in both these sets, right, every transaction output is used only once, is spent only once. What I may mean by double spending is the same. So here, right? So in this same thing, okay. In this case, two transactions list. If say Akshay has 5 bitcoins over here, he has 5 bitcoins, and he's sending it to Mahesh. This is transaction 3. Okay, and here instead of referring back to transaction 2's output, which is the 5 bitcoins, the remaining change, whatever Akshay got after sending 10 bitcoins to Ganesh, is referring to this 5 bitcoins. This is valid. But instead of referring to this, it is referring to the transaction 1, which is the same 15 bitcoins, out of which 10 was sent to Ganesh. This is wrong. This is not allowed in Bitcoin, even though uh, you can you can argue that it has 15 bitcoins, only 10 was consumed, and he is trying to spend only 5. The way Bitcoin works is whenever you spend an output, it can be spendable only once, which is it can be part of an input only once. And once that input is output is spent as part of an input, you generate new outputs or you generate new bitcoins, and only those would be present in the UTXO set. Okay, so it's just that this is how Bitcoin um, ensures that they don't they have that ensures that you uh, how do you say that when Akshay is sending some amount, he has that sufficient funds. Okay, so the key thing in Bitcoin is say when you have in the physical world you have a 1 rupee note, right? When you give it to some other person, you say, okay, say you have 100 rupee note, okay, um, out of which 20 rupees you are giving to some person, the remaining 80 you still have it in your hand, but in Bitcoin how it works is that is actually represented by a new transaction output. It's basically like you have 100 rupees, you give it to the tea shop owner. He takes 20 rupees for his own and he gives back the change 80 rupees. That 80 rupees is a new currency note actually. This is how Bitcoin works. Out of 15, when you say you spend 10 to Ganesh and remaining 5 you are having it to your own to yourself, that is the change output, and that is actually a new transaction output or a new Bitcoin which is created because of this transaction that you sent some money to Ganesh. Because of that only this 5 Bitcoin change was created, or this remaining change output is created. So this is how Bitcoins work. If you want to support this feature, right, say Ganesh is the same 15, if he wants to refer to and spend 5 Bitcoins means, you should follow something called as the account based model, where you will, instead of having a UTXO set, you will have a database where it specifies public key and like it will specify like a public key has 10 bitcoins balance, and when it says transaction 2 it sends 5 bitcoins means it will decrement 5 and remaining 5 will still be there, and in transaction 3 5 will still be there, like that. So that is the account based model. Here in UTXO model, they want to mimic whatever happens in the real world, how you have a wallet, purse, and all those things. So in the same way, they have these transaction outputs, and they have this referring back to the previous transaction output and ensuring that double spending doesn't occur.
Sir, Sai sir,
Yeah.
Sham. Sir, does it mean you want to say, sir, like one private key is there, so it is used for only one transaction? One private key cannot be used for, suppose you have used for one transaction, you cannot use for again for some another transaction. Is it like that, sir? You want to say?
So actually what happens is Bitcoin was created for anonymous transactions, like that, but what it really achieves is pseudonymity. Okay, why is the case is because in Bitcoin everything is in public keys only. So public key is your name actually in your Bitcoin network, and you can have just one single public and private key, and you can um, do transactions on the network. But say you want to convert that bitcoins into some dollars or something, right? You go to a, Bitcoin exchange platform or something. At that place, what you are doing is you will be giving your name, details, everything. And in that case, what happens is, say some agency, government agency, or someone looking at the transactions, right? What would happen is they will get to know that this particular person is the owner of this public key. And when they look at the, now with this new association, right? Say Shyam is the owner of this public key means, now if they look at the Bitcoin blocks, right? All transactions you are having this public key, right? They will get to know what all transactions you are involved in, and they will get to know how much amount you are spending in each transaction. since everything is open in the Bitcoin network. So usually what is preferred is, since generating new public and private keys are easy, right? You can just keep on generating new public and private keys to confuse anyone, and for privacy reasons.
Okay, sir. Thank you, sir. I have one more doubt, sir, actually.
Yeah,
Now, regarding this is fork, sir. Fork you explained earlier. So
yeah.
in that you told, suppose one fork blocks are created and that some transactions are there. So I think there is a chance sir, that some miners are there. They are creating blocks continuously. So intentionally they may they may discard some transaction. Chances then, sir, I think they may try to discard the transaction again and again. Is there any chance like that? They can do, na, sir, like that.
Yeah, yeah, yeah. They can censor some transactions. So if a miner doesn't want to, if a miner doesn't want to include any transaction coming from you, first he should somehow I try to identify that public key, in which you are involved, right? The to address or the from address, somehow we should try to find those out, and then he need not include the transactions. But that only, like say 2 or 3 miners or something, they can try to censor your transactions, but your transaction would be censored completely only if all the miners in the Bitcoin network come to a conclusion to boycott your transactions. If that is not the case, then at least it is possible that one miner would still be trying to use your transaction and include it in the block.
No, but suppose that miner is not able to create block. He's trying to add the transaction, but he's not able to create the block. Then what will happen in that case? The
Uh,
transaction will be discarded, sir. I think permanent
no,
after some.
transaction won't be discarded. The thing is, it depends on the that miner's hash rate and hash power and all those things. And usually, like censorship is difficult to achieve in a Bitcoin network. It depends on one thing is right. If you're it's easy to do censorship given if you know that association between the public key and those things, but we assume that 50% majority is honest, right? Majority of the hash power is honest. So based on that assumption, we are sure that at least after some time, your transaction will be included in a block. Don't just be discarded.
Okay, sir. Thank you.
And usually what happens is many of them would be not providing any transaction fee to the miner node who is mining the block. So when I tell transaction fees means when you create a transaction and when Akshay sends to Ganesh 10 bitcoins means he will be referring to a previous output, say his previous transaction output, which Akshay has control of, say 20 bitcoins, okay? And say Akshay wants to give a transaction fees or a voluntary tip of say 2 bitcoins to the miner who mines his who places his transaction in the block and mines that block, adds a block to the blockchain. Okay, so he wants to give 2 bitcoins. So in that case, the transaction input will be referring to this 20 bitcoin output, and the output of the new transaction is would be having 3 outputs. So the first one would be to Ganesh's public key, an amount of 10 bitcoins, and the second it will have just 2 outputs. The first one is Ganesh's public key, and the second would be Akshay's same or different public key, and it would be specified as 8 bitcoins. Okay, so here the input size is amount is 20 bitcoins, okay, which is your input, and the output is actually 10 plus 8, 18 bitcoins. Okay, and the condition for a transaction to be valid is input should be greater than or equal to output. Okay, so if it's equal to, right, if the output is same as input, whatever the difference between input minus output, right, that is the transaction fees. which the miner can take take it for themselves. Okay, so here this is 2 Bitcoin is the transaction fees, and usually what they do is say if transaction is not getting accepted or something, they will send out a new transaction which has higher transaction fees. So definitely then a miner would be incentivized, and he will try to include your transaction in the block.
Okay, sir. Got it, sir. Thank you,
Okay.
sir.
And with respect to double spending, when I mention it is the consensus code, right? Your public and private keys just will ensure that the rightful owner of that public key who is having that private key can only use the transaction output, but nothing more. It's all the nodes who come together and who validate a block which is being generated by a miner. And how they validate a block is they will see that that a spent transaction output or any transaction output that an input is being referred to should be present in the UTXO set. If it's not present, then the transaction is invalid, and the block containing the transaction is also invalid, and that block is not part of your or the chain having that block would be invalid. So say you have this blockchain like this, and here this block over here is invalid, and whereas this block is actually valid. So valid in the sense all the transactions over here are using an unspent transaction output only, but here I am using some transaction output which is already being spent is being referred to in a particular transaction. So, and there is a fork over here, and this block is valid. Now actually what would be the longest chain in this case? The longest chain would be this particular chain only. All the honest minor nodes and the full nodes would see the longest chain like this, because the longest chain is the valid chain. Here even though the height is 4, here there is an invalid block in between. So even though it is the longest, since it's invalid, every node in the network will not follow this chain. They will not add blocks to this invalid chain. They will start adding it to this block only. So it is double spending everything. All the nodes coming together only decide on um, decide on what a block is invalid and whether a block is valid. It doesn't rely on these cryptographic keys. Cryptographic keys main notion is to find out who the rightful owner is. Double spending is you found out the rightful owner, but that owner is acting maliciously and is trying to spend that same 10 rupee output or the 10 Bitcoin output to two persons at the same time. That is a fault, and that is avoided by consensus. But which of those two transactions gets added into a block, it depends on it's randomly decided. Say one transaction, say Akshay wants to sending the same 10 Bitcoin to Ganesh or Suresh, means either one of them only will be added. But definitely when one is added, the other one cannot be added. That is uh, achieved via consensus, and double spending is prevented. Okay. So any other doubts? Anyone in Bitcoin or Ethereum or anything, or soft fork, hard fork? Any doubts in those concepts? If you have doubts, you can unmute yourself and speak up, or you can post it in the chat box also. Okay. So has everyone gone through the understood what soft fork and hard fork is? If then, can anyone just unmute and explain? Or when does a fork occurs other than this two mining nodes mine at the same time? Other than that scenario, when does a fork occur?
So when two miners create the node at the same time, then fork occurs, no, sir.
Sorry.
When two miners, two or more miners, they create the block at the same time.
Right. Uh,
That,
that is the normal fork. Okay. But
yes, sir.
there are forks which get created other than that condition. So the normal condition is when two or more miners create blocks at the same time. That is eventually that would be solved, and that would be solved because they have the rule of following the longest chain, and after some time definitely one of those chain only would be the longest chain, and everyone would settle on that longest chain. So that would resolve automatically after a day or after some time. But there are other things due to which forks might occur. Any idea? You would have seen this in week 3 or week 4 lectures, I guess. Any guess?
No, sir, nothing like that, sir.
Okay. So the thing is, when we say that every node in the network, in the Bitcoin network, has to be in consensus, right? There are two things which they have to be in consensus. One is this UTXO set, okay, and the second is the validation rules. Okay, so by validation rules, what I mean is uh, transaction validation. So whether a transaction is valid or not, what are the rules for that? The transaction input should be a script sig and that amount. The transaction output should be some script output key, and the sum of inputs should be greater than or equal to the sum of outputs, and this transaction should not be using any unspent should not be using any spent output, right? All these are rules which validate a transaction. And the second thing is block validation. So block validation is what's the size of the block which is allowed, the number of transactions which can be placed. So a size of the block is 2 MB, and a block should contain only valid transactions. And so these are all block validation rules. Okay, like that set of rules, and also that proof of work, which is less than the target value. So all those things, all the rules, validation rules. Now it is any software program, right? Say your operating system or any application. Now there won't be a case where say you install a application, and you will be using that application, the same application throughout your lifetime as it is. Definitely there will be upgrades. Okay, so say like there will be like some security attack or something, and you want to upgrade your software, or you want to improve the efficiency of your software application. So in that case you want to change the code, or you want to all those things, so for security reasons, okay, or to improve your performance, anything. So for all those things you definitely would be looking to upgrade the application. And the same way, the Bitcoin is also a huge like software thing, right? So it has all these validation rules which is implemented in software, and all this is part of a software code. Okay, so in that case, say you I want to improve the transaction throughput, as in more so if you take your Mastercard or Visa, it there are around like 10,000 or 1,000 transactions per second. Okay, so 1,000 transactions per second get so many number of transactions, 10,000 or 1,000 something, so which is definitely more than the one block per 10 minutes. Okay, so if I increase the block size, right, say now it is 2 MB, and if I increase the block size rule, which is say instead of 2 MB I want to now include 10 MB blocks. So by increasing the block size, indirectly what I do that what I mean is more number of transactions can be included in the block, and by that thing what happens is my transaction throughput will increase. That is, there will be an increase in the number of transactions which are confirmed in every block, so my transaction throughput increases. So if so my I'm changing the validation rule for the block. So previously only 2 MB blocks were accepted, but now I would be accepting 10 MB blocks also. So for all these things, every node in my Bitcoin network should follow the same validation rules. Okay, and if a set of nodes do not want to upgrade to this 10 MB rule, then what happens is there will be a fork happening. Okay, so how you change these validation rules, or how you change these rules, right? Whether it's backwards compatible or not, differentiates whether it's a soft fork or a hard fork. So a fork, till now you would have just viewed it as two blocks mining at the same time, but that is not the only way a fork might occur. That is actually a safer fork because it will be automatically resolved by all the nodes. But here, if you change, upgrade your software, or upgrade your rules, or add more rules or something which the other nodes do not want to follow, the other minor nodes or other full nodes, then there will be a split in your blockchain. So if we want to take an example, right, say initially your block limit is 2 MB, okay, and now my this is my old block limit, and the new block limit, say it is uh, say 1 MB. Okay, now what happens is, assume that all the blocks in say you have the minor A set, so minus A and minus B. Okay, and minors A are following the old block limit, and minor B are following the new block limit. Okay, and what will happen now is, uh, initially all the blocks, say uh, till block 4, okay, till block 4 all the um, till block 4 it was the old rule is still being used, as in the software, the rules upgrade hasn't taken place, and at this point over here, this new block limit, that is it should be less than 1 MB, is specified. So less than 1 MB is specified over here at this place. So now what happens is, you have two different set of miners, Okay, so one miner is having following the 2 MB block size, and miner B are following the 1 MB block size. Now what will happen is, assume now you will have two conditions, two scenarios. One scenario is scenario 1, if miner A is majority and the nodes which are following the new block limit are minority. Okay, and scenario 2 is the opposite. A is the minority and B is the majority. Okay, in scenario 1, first let's look at scenario 1. In scenario 1, what will happen is, A will be sending in new blocks. Okay, so let's assume this all less than 2 MB blocks is represented by this color block, and all which are less than 1 MB is this blue color block. Okay, since A is say like now uh, miner B is following set of the B set of miners are following the new limit, and they add a new block over here, the 1 MB block, and now this block will be part of your blockchain only if majority of the nodes accept that the block pass the block validation rules. Okay, now what the majority, so we are now following scenario 1 over here. Okay, so the majority is following minus a rule only, which is 2 MB limit, and now we added a 1 MB block. Whether it satisfies the 2 MB limit or not, can anyone say? If you are following me, it's evident. So whether this block less than 1 MB is accepted by all the nodes.
Yeah, it is satisfying, like less than.
Good. So this all the blocks which the new set of miners following the new rule, what all blocks they uh, mine, right? All those would be satisfied by the old nodes also. Those following the old nodes. Okay. So because it's still less than 2 MB. But since A is the majority, right? The minus set of A, they will now try. They will now what they will do. They will accept this block. This gets confirmed. Okay, this gets confirmed. And now what miner A will do is they will add a new block over here, and this will be having less than 2 MB. Okay, and now what happens is now what will happen, say the B set of minor nodes. Okay, they will look at this block, and they will see that it's not less than 1 MB and this is an invalid block, and they will reject it. But for all the nodes following the old block limit, this node is still valid because it's less than 2 MB only, and this will be valid with respect to all the A set of miners, and they will be looking at this as the longest chain, and they will try to add more blocks either of less than 2 MB or less than 1 MB. Okay, say this is of say 1.7 MB this block. So the B set of miners would reject it, and they will try to add a new block to here, which is less than 1 MB. Okay, so like this it will get split, and they will keep on adding. Okay, um, so according to the nodes following the new block size limit, this chain over here, if it has a block which is having more than 1 MB, this will be invalid for them. Okay, and this and this would be the valid one. Okay, so this is the scenario 1, and what will eventually happen is, when say since A is the majority, the nodes which are following the um, old block nodes which are following the old rules, right? They can actually they can add blocks either to this chain or this chain, because in both these set of chains in the fork which occurred, less than 1 MB is still satisfied less than 2 MB limit. Okay, so the old nodes which don't upgrade to the new rule, they are still um, uh, they can still generate blocks. They will still accept all the blocks, and for them both these chains are valid only. So with respect to miner A, this chain is valid and this chain is valid, but for miners B which are following the new rule, only this chain is valid. Okay, so this is what occurs in the scenario 1, and eventually what will happen is only one of these chains would be the longest chain, and the longest chain would only be set as valid, and since the nodes which are in the minority, right, they can either try to just follow the new the valid chain according to them, but they will realize later that okay, the other set of nodes haven't upgraded their rules or something, and what they can do is they can either try to enforce that rule is compulsory or something like that, or they can um, neglect the other longest chain and deem it as invalid. Okay, so that's the scenario 1. In scenario 2, what happens is, since the B is the majority, right, since the blocks which are having the following the new limit, they are the majority, what will happen is the ones which are less than 1 MB, all those blocks would be produced more frequently, and the blocks which are produced by the set of A miners, which is between 1 to 2 MB, those would all be rejected and they would be produced less frequently because their hash power is less. And in that case, the old nodes which are yet to upgrade, or so when I tell they are yet to upgrade, either they know the rule but they don't want to upgrade the rule, or they don't know that rule is still there and they don't want to upgrade it. They don't know the rule and they are not aware of the rule. Okay, so two classes are there: they know the rule and they don't upgrade, or they are unaware of the rule. So the ones who don't want to upgrade, they will be in a separate chain, but they can still contribute nodes, they can still contribute blocks to the for them the new chain is also still valid for them, and they can still contribute to the new chain, but only a subset of blocks they can contribute. But finally what happens is, the longest chain would be the one which follows the new rule, because they represent the majority hash power, and if they want to have financial gain or something, right, they have so much of bitcoins there, then in that case the nodes which are not which are not yet upgraded, they will upgrade to the new rule and join the longest chain and start mining on it. Okay, so that will happen in scenario 2 eventually, and whatever we discussed till now, that is known as soft fork. What we mean by soft fork is, um, when you have an old rules and when you introduce a new rule, when you change a new rule or something, right, you tighten that existing rule and you don't introduce a new rule just like that. So the thing which soft fork is mainly done is for backwards compatibility. And when we tell backwards compatibility is, um, all the old nodes will still accept the new rules block, the blocks following the new rules. Okay, so by enforcing that this backwards compatibility, what we achieve is, um, in Bitcoin the main important thing is with respect to how much security, how much hash power is honest. and the assumption which should always be there is majority of the hash power should be honest. And in backwards compatibility, since all the nodes, okay, irrespective of whether they upgrade to the new rule or they stay with the old rule, irrespective of that, the in a soft fork, the rules are just tightened in such a way that all the nodes will can still accept the new the blocks following the new rules, but the vice versa is not possible. But still the old nodes following the old rules, they can still accept the blocks following the new rules. Okay, so in that case they can still participate in the network, and they have the choice of upgrading the rules. And the hash power is not split. Okay, that can be thwarted in soft fork. So that is what they mention in soft fork, which the fork happens, but it is not permanent. As in, the old nodes can either they can switch over to the new rules when they see that how much ever blocks they produce using the old rule using the old rules, they are being rejected by the nodes following the new rules. If the case that that scenario 2 occurs where the nodes following the new rules are having majority number at their majority hash power in their side. Okay, so this is what soft fork is. And hard fork is when the rules are written in such a way that a rule is changed in such a way that any node which is following the new rule, if it generates a block, it will be outright rejected by the nodes following the old rules. Okay, so the case is say you are increasing the block size limit. In that case, initially it is 2 MB. Now if I am creating a block which is more than 2 MB, it will always be rejected by the nodes following the old rules. And if you have a scenario like whether the majority is following the new rule or old rule, right? If the majority is following the old rule, what happens is um, there will so if again two scenarios, whether my new rule the nodes following the new rule are the majority or they are the minority. Okay, if the nodes following the old rules are in the minority, what happens is my longest chain, as in the longest chain would be the one which is following the old rules only, because it represents the majority hash power. And in that case, what the nodes following the new rules will do is they will see that this chain to be the longest chain, and they will all start mining on the old rules chain itself. And the old rules chain will be the longest chain. Okay, because um, we are just relaxing the rules. That's what hard fork is all about. Okay, the blocks with the so when I tell relaxing the rules, the old rule is less than 2 MB, whereas the new rule is less than 4 MB. Okay, so the blocks, the nodes following the old rule would reject the blocks which are 2 to 4 MB, but the nodes following the new rule, they will accept both these blocks. And since the majority of my hash power is following the old rules, right, the longest chain would be the chain following the old rules, where all my blocks would be less than 2 MB. And since the nodes following the new rules, for them less than 2 MB is also a valid block, they will start mining on the chain which is which is being populated by the nodes following the old rules, and they will start using that chain only. And what eventually happens is this new rules, whatever they try to enforce, right? They the like those 4 MB blocks, when they try to add it to the longest chain, those would be rejected by the majority nodes which are following the old rules. And by chance, if the new nodes following the new rules, they come up with a block less than 2 MB, that gets accepted by the nodes following the old rules, and they will be added to the longest chain. And in this scenario, what happens is the um the the nodes, the new rules is not propagated at all, and all the blocks which are there in the longest chain won't be following the new rule, which is less than 4 MB. But say you have the scenario where majority of them follow the new rules. What happens then? So here you have just one chain only, and that longest chain would be following the old rules predominantly because it represents the majority hash power. But here, say the majority hash power are those following the less than 4 MB limit, which is the new rules. Now what happens is, um, say these are all for less than 4 MB blocks, and these are all uh, less than 2 MB blocks. Okay, since the majority are those following the new rules, definitely the longest chain, the higher success probability of the longest chain following the new rule would be much higher because they represent the majority hash power, the nodes following the new rules, which is less than 4 MB. So the longest chain the um, will be having blocks which are following this new rule of less than 4 MB. Okay, whereas um, the old nodes, right, they won't since they are not upgrading, they will see this new longest chain as invalid, and what they will do is they will not mine on this chain, but instead they will create a new chain and they will continue mining on it, even though that new chain is represented by the minority group of nodes following the old rules. But for them it is the valid chain, and that will be the valid longest chain for them, which is having all less than 2 MB blocks, and they will still continue mining on it. Whereas the new nodes which are following the new rules, for them both the chains are valid, but the ones that are having less than 4 MB, the new rules, those are part of the longest chain, and they will be mining on that longest valid chain. So you have got a split over here where all my majority of new nodes, the majority of new nodes are mining in this chain, whereas the minority of the old nodes are mining on this chain, because for them this is invalid. Okay, and like this it will keep on going, and what eventually occurs is there is a permanent fork happening, a permanent split happening, and this is what is termed as a hard fork, and the fork cannot be reversed at all, because unless all the old rule nodes upgrade to the new rules, until then you cannot delete this fork. And what eventually occurs is, when majority of the nodes follow the new rule and minority is still following the old rule, means you generate a new cryptocurrency. So initially, say the new rule nodes are the majority, they will have Bitcoin, and the real life example is Bitcoin got split into two, and the one is the original Bitcoin which majority of them accepted, and minority of the nodes didn't accept the new rules, and they are in a separate chain, and they term it as Bitcoin Cash. So this hard forks generate new um, a new cryptocurrency out of nowhere. So that is what hard fork is all about. And the thing with the security problem with hard fork is, since the 50% more number of miners, diverse miners should be there, and majority of them should be honest. That's what the security assumption on which Bitcoin's consensus and everything relies upon. And now in this minority chain, which is represented by the old rules, the nodes following the old rules, they are the minority hash power. And now in this new chain, out of that minority, 50% should be honest. And an attacker who has substantial computational power would be it would be easy for an attacker to gain majority hash power out of this minority group and try to uh, do double spending or try to discard some transactions and erase the blocks in this new chain. It would be relatively easier since the nodes following the old rules got split and they are actually even uh, uh, the hash power is significantly lesser after a fork occurs. So that's the disadvantage of a hard fork. When you compare this scenario with a soft fork, when a majority of nodes adopt the new rules, what happens is by ensuring backwards compatibility, the chain which the new rules the chain having the new rules blocked, right, they will still be valid for the nodes following the old rules, and the permanent fork does not occur. Whereas in hard fork, when a majority follows the new rules, the old rules will not see that as the longest chain, they will see that as an invalid chain, and they will start a new chain itself. So that is what soft fork and hard fork is all about. And a combination of both are possible. As in, when I do an upgrade to a software, when to the consensus rule or Bitcoin software, um, there will be two rules. One rule would be backwards compatible. The other rule would be it won't be a backwards compatible rule. So in that case, so there are so many complications when you change validation rules, and it is sort of this hard fork and soft fork is should always be looked into whenever you change these validation rules. Okay, and a quick like a trivia note is like the all the latest blockchain platforms like Tezos, right? They have something called as the voting system, where before they want to change any rules, they want to change any consensus rules, they will send out an voting scheme or something where all the miners and all the nodes can cast in their votes, and everyone can then say for like 2 months or something they will keep the voting stage open whether to increase the block limit or reduce the block limit. And if all the nodes should send out a transaction, whether they support the vote against or for the vote, for the proposal. And if majority of them are for the vote means, then they will implement that consensus rule after that time period, and everyone will follow the new rules. So in Bitcoin, that facility is not there as like inherently that facility is not there. Currently, they use something called as the upgradation policy, where they try to some space is there in a block. In every block, the miner adds to the blockchain. So within that 100 byte space or something, they cast their vote or something whether to upgrade or not. But that is not fully. That is something which they are now using. So for using that itself, they had to change the consensus rule, or they have to change those things. But in Tezos blockchain and all these latest blockchain, the upgradation policies and all those things are inbuilt as part of the consensus code itself, and it's much more safer. Okay, so any doubts with respect to the soft and hard fork? It's like very confusing if you um, just try to understand, but the key point to take away, the key takeaway is what will happen when majority of nodes follow the new rule. In a soft fork, when majority of the nodes follow a new rule, the minority of nodes which are still following the old rule will still accept blocks which are being produced based on these new rules and mine on the longest chain. But in a hard fork, when majority of my nodes follow the new rule, the minority nodes following the old rules will not accept those blocks following the new rules to be valid, and they will create a new chain and mine on that chain following the old rules only. So when a majority of nodes accept a new rule in soft fork, the longest chain, there won't be a permanent fork. A fork might occur, but whatever the longest chain is, all the nodes would be on that longest chain only. But in a hard fork, when a majority nodes follow the new rule, the minority nodes will split off and there will be a permanent fork happening. So that is what soft fork and hard fork is all about. And in Ethereum, ironically, any upgradation rule or anything they do in Ethereum, they try to do it as a hard fork because they want the all the users, all the nodes to upgrade to the new rules. And why they do that is, why they prefer hard forks in Ethereum is, instead of having it backwards compatible, all the new rules that are actually being rolled out in Ethereum is actually improving performance or improving security, and it is useful for everyone to follow the same rules. So in that case, by having hard fork, they force everyone to upgrade to the new rules. And if they don't upgrade, right, if the minority nodes don't upgrade to the new rule, what happens is this permanent fork occurs, and only the chain following the new rule would be deemed as the actual main ether cryptocurrency. And the minority nodes, they either they are forced to move to the new rules, or if they still are in the old rules, right, they generate a new cryptocurrency, and that will have a lesser economical value when compared to the majority of nodes following the actual new rules cryptocurrency. So financially it would be they would be it would be less for them. They are at a loss actually, the nodes following the old rules. So this is what happens, and in a soft fork and hard fork. So any doubts in soft fork and hard fork? Okay. So in that case, any other doubts you have other than these things?
No, sir. Sir, this fifth week doubt you will clear in next session, sir.
Fifth week doubts. I didn't get it.
Fifth week lectures, no, sir. Fifth week. Uh, this ongoing week. So those doubts you will cover in next week, or
Ethereum, is it?
yeah, Ethereum and Ethereum, correct.
Actually, I didn't see any doubts on the forum, so I don't know like what doubts you have.
Okay. Actually, I also have to go. Actually, I covered only one or two lectures only this week, na.
Right, right. Yeah, so what I suggest everyone is you go through the lectures for week 5, and post your doubts on the forum. I'll answer those, and then next week I will concentrate on Ethereum, uh, how it is different with Bitcoin protocol, and what is smart contracts, and what do you like, what protocol, the proof of work or the consensus code, what all is being used in Ethereum, Okay, like compared to Bitcoin, I will try to concentrate on this.
Okay, sir. Thank you.
Okay, so if no more doubts, then I guess we can wrap up the session. Thank you everyone for attending. Thank you for making it interactive. See you all in the next session.
Thank you, sir. Thank you so much.